Hey, welcome back. I have a very quick little machine update that I wanted to share. Here on the Deckel FP1 milling machine, I usually use the indexing head because it's a very good way to mount very different accessories, starting from collets in the bore, from a vise or a 3-jar chuck on top of the large flange mount here, or even stuff like an Arova chuck in the 40 taper socket in here. Problem is, I like to use cutting oil on this machine. I set the flood coolant in this machine up with cutting oil. I removed the water-soluble coolant because it will cause trouble over time. It will create rust and go bad probably. So I drained it, cleaned it out, flushed it, and then I filled it up with Yokish Alpha 93 cutting oil, which is not ideal for a recirculating system, but I wanted to try it. The problem with the indexing head especially is if you run coolant, the coolant will get inside and rust everything of the internals away. That's a known problem with the indexing heads and the Deckel rotary tables, the large 380mm rotary tables. With cutting oil, that's less of a problem because cutting oil does not cause rust. But still, you want a way of containing the cutting oil. Deckel used to make a large pan that you can hang under the indexing head to contain some of the cutting oil. But still, that means that cutting oil will get all over the upper side of the indexing head here, which is rather annoying. You would like to prevent that. So I was playing around a little bit with some ideas, and I came up with this. This looks like a frying pan with a hole in the center, so it's a frying pan for donuts. And the dovetail. This fits over the spindle of the indexer. It has a hole back here, with port out the underside, and I 3D printed a small adapter piece that just is a tight press fit. And the dovetail mates with the dovetail of the cover of the top of the indexer. Normally the overarm support for using the tailstock center or the dead center of the indexer goes here. But we can use this also to mount other accessories. This is just a very snug fit on the dovetail. And I can drop it down over the spindle. It's kind of center-ish. Lock it in place. And I also took some TPU, flexible filament, for the 3D printer. And I printed a gasket that sleeves around the spindle of the indexer like this. This should keep most of the cutting oil out of there. I have still access to the entire mounting flange for the accessories and also for the 40 taper bore in the center. The connector back here connects to a hose that redirects the cutting oil back into the sump of the machine. This could have been printed a little bit smaller, but it does well. This is just a test. Final part could be machined from aluminum or even be an aluminum casting. So with the pan in place, okay, quick look into CAD. This is the oil pan or drip pan as it's designed in Fusion 360 with the dovetail to interface to the indexing head, and over here is the fitting for the hose. As I have shown, the fitting is a separate piece, so this entire pan prints without supports on a regular 3D printer. Same for this hole here, it's designed in a way so it doesn't require supports. This conical shape here is steep enough so it prints without overhang. The interesting detail might be the TPU seal in here. It's designed in a way so it only makes contact up here at this edge. It's like a knife edge. And it has an undercut in the oil pan here and a kind of mating geometry on the TPU seal. Not sure why I decided to not model it properly. But that way the seal snaps over this undercut and stays in place and doesn't walk off. Yes, of course, you could just design a off-the-shelf sliding seal or a O-ring into this oil pan, but who has a fitting oil ring on a weekend in his shop? I don't. Also, I didn't have O-ring stock to make my own O-ring this size, so I decided to give a TPU seal a go, and that was a great learning opportunity. And the seal works so far quite well. And make sure everything is clean, especially the face of the indexer. This is a register surface for the flange that goes on for the large chuck. Good idea to hit it with a stone very quickly, just to make sure there is nothing causing problems. And then we drop the chuck on here. This is not a super tight fit, but it always wants to cantilever a bit and gets snugs up. Then you just have 4 set screws on the circumference that lock into mating spots in the spindle. And now I think you get the idea of what I built here for a prototype. I mean, this is not the final version. For example, just notice that a normal Allen wrench doesn't fit in there, using a cutoff one here. But that's why we do prototyping. Once I get a final version, I might make the 3D model available to everyone who wants to print one for if you have a similar milling machine. But in all honesty, this is an easy enough part to 3D model yourself if you want to have something like this. Okay. Now when we run cutting oil on here, oh yeah, this looks serviceable. A lot is going through the through bore of the indexer, of course, which is not a problem. But also there's a lot going through the pan, through the hose back into the casting. I like this. But just as with coolant, you have to use it with caution. If you, for example, aim the cutting oil directly at a large diameter fast spinning cutter, you will get overspray into the entire shop, as it's normal. But for example, I did some work with a 8mm T-slot cutter yesterday at 1000 RPM, and that was not a problem at all. Very little overspray, very controllable. So I think this is a decent solution. To contain the oil from the through bore, I just turned the plug from Delrin and a piece of hose that goes down into the pan, the oil pan of the milling machine, just so it doesn't dribble down and splash on impact. So I really like the solution so far. So especially when cutting tougher materials like stainless steels or tool steels, running a constant stream of coolant, or in this case lubrication, can be very beneficial. Cutting oil, of course, has its drawbacks with very high surface speeds because it will burn and smoke very much. But on lower surface speed operations, like here drilling with a high-speed steel drill in 316L stainless, the cutting oil does a wonderful job. It's not smoking at all, the surface finish is improved, the tool life is improved a lot, and also the general chip formation has a great benefit from running oil. It's a little bit more mess, of course. You have a little bit more cleanup, parts cleaning, a little bit more effort. But I think from my vast experience of 2 weeks running the flood oil on the lathe and the mill is overall positive. Tools like this high-speed steel piloted counterbore that are run at a little bit slower surface speed also benefit from the cutting oil a lot. These tools are not extremely cheap, and you want to make them last as long as possible, even if you have the option to regrind them yourself in the shop. It's a major headache to grind them, and you want to get the most out of them before you have to resharpen them. Also, the surface finish of the counterbore is just nicer if you have good lubrication. Even lubrication from a oil bottle is already better than nothing. This is cutting an O-ring groove with a 3mm carbide end mill under flood oil. Oil is generally not regarded as good in cooling, but the lubrication is vastly better than on coolant, water mixable coolant. Also, it's usually considered not as good as washing away chips, but as you can see in this case, the stream of oil is doing a very good job of washing away the tiny chips from the end mill off to the side of the workpiece. Running the end mill at 2000 RPM and down feeding like 0.1 millimeters per full revolution of the workpiece. So I'm basically manually helical interpolating this groove. Once I'm at full depth, I'm stepping over and cutting it to final width and size. The general idea for such a oil pan around a rotating indexer spindle comes from, I saw several gear hobbing machines that use a very similar setup, and that inspired me to do this, to try this at least. It's 3D printed from PLA, really very basic. PLA has proven to be extremely resistant against oil and solvents. Same for the TPU. I've yet to lose parts printed out of TPU or PLA to oil or solvents. Normal shop solvents like alcohol or acetone. Oil doesn't seem to attack it either, so it's fine. Oh, and when you run either flood coolant or flood cutting oil on a machine, you get pretty good at this. The foot rag. One thing that I didn't like was the hose coming out of the central bore of the indexing head. The hose always has kind of a shape to it and wants to snake in a certain direction, and when you spin it you get this trailing circle of oil that extends out of the base casting of the machine. I could add a weight to the hose, but then when you drop the C-axis down enough, the weight hits the deck here and the hose does whatever it wants. So I kind of got reminded back to when I was a child. I saw very often gutter chains from on a house to keep the splashing of the rainwater a little bit more under control. And that's exactly what I did. Took a piece of, I had some stainless chain, piece of hose, zip tie, and the same Delrin adapter into the bore of the indexer as before. And when I run cutting oil now, it runs down the chain without much splashing. And when I rotate the indexer, it just follows along, which is very nice, very controllable. It would even work with the indexer at an angle, then the chain would just follow. And when I raise or lower the C-axis, the chain just coils up down there on the deck of the casting. So I think that's a decent solution. And the oil pan up here seems to work fine too. So I'm quite delighted about how well this works. It took me one prototype of this piece that I threw away, and this is kind of the final iteration already. So I hope you liked this. I hope you enjoyed this little information dump. Thank you all for watching, and I'll be back.